Welcome. This lecture is called Matrix Operations. So matrices are two-dimensional arrays of numbers. This is a mathematical term to describe numbers that are stored. When we say two-dimensional arrays, we mean that you need two things to describe elements of a matrix, and those things involve the number of rows and the number of columns. So here the letter M denotes the number of rows, and the letter N denotes the number of columns. This is a very standard notation. So rows are going to be, these are sketches. So this is rows and columns, and here also rows. I'm talking about this part here of this array, and also over here columns, and here columns and rows. So these are sketches of basically three types. In general, we would say, when we say that the number of rows is m, the number of columns is n, we are referring to matrices. The way they look like is they look like rectangles. Okay, so you could think of these two-dimensional arrays of numbers as rectangles of numbers or tables, right? So this is a very common way of referring to matrices in the real world when we have data sets, and these data sets store uh, characters or numbers. Then in a given file, for example, an electronic file, well, even if it's a hard copy paper file, these so-called matrices are also going to be things that look, objects that look like tables, right? But they look like rectangles, like here. So in the first illustration here, what we observe is that the number of rows is bigger than the number of columns. That is the scenario for this matrix. In the second scenario, we have that the number of rows is smaller, so the number of columns, here the number of columns, exceeds the number of rows. Okay, and in the last scenario we have that there is as many rows as there are columns. Okay, so sometimes this is when you would say that m equals n. So in this case you would say there is n rows and there is also n columns. Okay, but in general we use those two quantities, rows and columns. They are referred as dimensions, and that's why we say this is an array that is two-dimensional. Thus, this set of matrices is denoted as M sub M and N. So here are some examples. M sub, you say M sub 23 or M sub 51. Numbers like that. The indices are two indices. Well, this denotes M sub Mn denotes the set of all possible arrays, all possible rectangles that have m rows and n columns. And the formal name is for that set is a vector space. Okay, here we assume that the entries, the numbers that are stored on each of these locations. Say, for example, here is a column, and let's say that here is a row, and so the number that's stored right there, we say this is column J and this is row I, and we say that this matrix is called A. So then this entry here is going to be referred as the entry sub A sub I J, right? So the name of the matrix, the name of that two-dimensional array, is going to be typically an uppercase letter, and then if we're referring to specific values stored in certain locations of that array, we would use a sub-index that is like a sub-index with two uh, sub-indices, right? Something in this fashion, so that we can specify the number of the row and number of the column. Okay, so one thing we'd like to get out of the way here, in a very similar spirit to what we did with vectors, is to establish how do we say that matrices are equal to each other. Um, well, first, if we're comparing two matrices, we have to note that the number of rows and number of columns have to match, right? To consider one matrix to be equal to another, then their dimensions have to match. That means that if you take a quick glance of one of them, so here's, say, for example, A, the other matrix you're comparing it against, say B, has to have the same type of shape. Okay, it is possible, could potentially, for these two to be the same, but if you were comparing A versus another matrix, I'm gonna draw here, say matrix D, from the start, you see, from the start, it's not possible for A to be equal to D. Why? The number of rows of D is completely different than the number of rows in A, right? They don't match. It's not the same. They simply do not match. A has more rows than D. That's something that we can tell right away by just looking at the shape of these rectangles. So we would say there's no way that A equals D. But if they have the same number of rows and the same number of columns, yet there is an additional requirement they must satisfy, and that is that every entry, every single location, every number on every single location, for every row I between 1 and m, and for every column j between 1 and n, you must have that the entries match. So the 1 1 entry of one matrix has to match the 1 1 entry of the other matrix. Say here's a matrix A with entries, I don't know, 1 3. Well, that has to be exactly equal to the 1 3 entry of the other matrix B, and so on. Right? So that equality on every entry has to be true for all entries, and if so, then we would say, oh, then the matrix A is exactly equal to the matrix B. The other thing we would like to do, this is defining operations, very basic operations, is to establish how we define the sum or the addition of two matrices if these matrices are members of the vector space M sub Mn. And one thing to note is that we're going to require that for both of these objects to perform the operation we call addition on these objects, we still require, like in the previous definition, that they have the same dimensions, the same number of rows and the same number of columns. In other words, when we compare the shape of each of those rectangles, it has to be clear that the number of rows of one matches the number of rows of the other one, and the number of columns of A matches the number of columns in B. That's to start. And then to be able to write an addition sign between these two things, we know that there will be a matrix called A plus B. This is going to be considered the new matrix. And the entries of that new matrix, the matrix that results from adding A to B, provided that A and B have the same number of dimensions, that are compatible, the entries of that new matrix are defined by going and adding individually scalars. So if we want the entry in row I, column j of the matrix A plus B, we go to the matrix A, take a look at the scalar A sub ij, take a look at the scalar A sub ij in matrix B, and then we add them together. So this is in symbols. It sounds much more complicated than it really is. Here we have an example. Matrix A is a matrix that has 2 rows and 3 columns. Matrix B also has 2 rows and 3 columns. So because the dimensions match, they have the same number of rows, the same number of columns, we're good to go. So this A plus B is what will be considered the new matrix. And to add them together, so here's the matrix A, here's the matrix B, and now to obtain the matrix that's going to be considered the new matrix A plus B, what we do is go to every location. So take a look at location 1, 1 in A and location 1, 1 in B. So we add the elements, the entries that are in location 1, 1, and precisely that those are going to be the numbers that are going to be stored on location 1, 1 of the new matrix. So A plus B, you would say something like A plus B and location 1, 1, row 1, column 1, that's going to be equal to the number 8. Okay, and that follows from adding 2 to 6 because these numbers are in row 1, column 1. So we continue, we would do that for every single entry, right? Same thing for entry in row 1, column 2. That's by taking this number, minus 3, and adding that number to positive 2. And in row 1, column 3, we'll take the number in row 1, column 3 of A, row 1, column 3 of B, and that's how we obtain 4 added to negative 4. Therefore, the new matrix A plus B has these entries. You can see how this number results from adding minus 3 to positive 2, and when you add 4 minus 4, then you get 0, and similarly for the entries that are on the second row.